Hi, this is Mike 0 Sierra November Zulu. In the last video I did a walkthrough of the latest Pycom Radio Controller features and introduced you to the AI or machine learning signal identification and classification. Today I just wanted to give you a quick demo of how you might use Pycom to train your own models. So you should see a Windows VM here on the screen. I'm going to run in Windows today. So first of all, if I just start up Pycom Radio Controller, I'm using a development build, so I'm not gonna run the executable. But this is the latest version that I have running. It will soon be released. It's got a whole change in the way that I add data augmentation to the machine learning classifier. But you can see I've just got Pycom running here, and under the settings menu in configuration, you'll see this signal detection tab, and down the bottom of it, if I scroll down, you can see that I have the ability to download training resources and reload the signal classifier model. So I'm just going to click the download training resources button there, and you can see that there's a warning box that pops up that says it's going to copy the latest model and scripts and documentation into your Pycom directory, and anything that was there previously will be overwritten. So if you have trained a new model, you might want to back that up first. But I'm just going to click yes there and copy the model in place. So we don't need Pycom for now. If I just minimize that. So one of the first things, actually I'll bring it back. I'm going to open up the website documentation. Just bear with me. So if I open up my website, you'll see on the Pycom website that there's plenty of information about this. If I come down to the AI signal identification page, you can see there's a whole lot of information around signal detection, but also the signal identification, which is what we're talking about here, and how the classifier works. So there's a lot of information there that you can read later if you're interested in understanding a little bit more about it. But also, what I'd like to draw your attention to is this logbook page. Let's just make it a bit more visible. So I've got some information here around my thinking around signal classification, and I had another post here earlier. Oh, no, not that one. I had another post earlier here around data augmentation. So I've thought about two different approaches. The first was based on some signal classification that had already been done in 2018, 2025, where these guys started training signal classifiers in a lab, and what they found was that the lab signals were not as good as weren't good enough to understand to predict what was coming over the air, because it was too clean in the lab. So they decided to add a whole lot of stuff around augmentation. So they would do things like amplitude scaling, make it stronger or weaker, put some noise in there, change the frequencies, and other things to mix up the signals that they were training their models on, so that they could more accurately classify a signal coming in over the air. I thought about this and I decided against it. I didn't like the idea of the idea of creating images for the CNN to train on that weren't real, and so I moved away from their thinking, and with the help of AI, I've come up with another approach. So there's a bit of detail on this logbook here where you can see I've decided to add additional data augmentation to the model as it gets trained on the signals you capture. So it uses these seven features of the signal to put metadata around each capture. So how flat the signal is, how spiky it is, number of peaks, the repetitiveness of the signal, how wide it is, how far off the center frequency is, and how strong it is on a time-based view. So by adding these additional training data augmentation to the model, it becomes more accurate. So if I connect to my radio and look at this beacon here, you can see it's putting out JT65. I know that's what it's doing at the moment. So if I do a signal capture and see what the model comes up with. Now it's detected the signal. It's not really wide enough. Let's ignore the automatic signal detection and see if we can get the model to report on that signal more appropriately. It still thinks it's FM, which is incorrect. So I could tell the model that that's JT65 and save that as a capture in my Pycom directory. So if I again open up the Pycom directory, you can see that we've got this signals directory here. And inside that signals directory, I've got this captures directory here. And this is a NumPy zip of both the scope image and the auxiliary data that's been captured around those captures. And as you can see, my latest capture here was the JT65 capture. So I've captured that signal over the air, and what if I want to update my model to take advantage of the fact that I know a little bit more, or I've captured more signals and I'd like to add them to my training data set? Well, in Pycom you can easily do that. So if I minimize this and open up a new tab here and open up my notes. So inside the signals directory, there's also documentation that was downloaded as part of that model on this signal identification markdown document, which I'll open up in Obsidian. So you can see there's a pretty big document here around what is signal detection and classification, including the section around model training. And you can see here that I've built into the application the ability to be able to train your models. You have to set up a development environment for this. I didn't want to include the torch libraries and other stuff inside Pycom because it would become a much larger application. So because this is an advanced feature, I've left it as something for people that are interested in doing it. A lot of people won't be interested in doing this, but for people that are interested in doing it, to install them in a zero environment. So the first thing you need to know is that you need to have Python installed, Python 3.1, ideally something more, installed on your environment. And then you need to add these libraries using the Python installer pip to your Python install. Obviously, you should probably use a virtual environment. I'm not going to bother at this point, but if I just copy that command there and paste it, you'll see that I've actually already got these libraries installed. So it's not done anything, but I mean, if I didn't have those libraries installed, it would have gone away and installed those libraries on my system. Now, further down in the document, you've got some different options around training. So Obviously, you can create a model from scratch if you have, hundreds or thousands of captures that you've successfully captured using Pycom. You can create a new model. A lot of people won't necessarily have that amount of data or that data available. I've been adding captures constantly since I built this into Pycom, and I've got something like 500, 600 different captures. My local amateur radio club has graciously said that I can use their remote radio to send signals over the air and capture them. I haven't got my hands on it yet, but hopefully soon I'll be able to generate my own signals over the air and build out that data set a lot more. But obviously on the 2 and 70 centimeter bands, the amount of it's quite quiet and there's not a lot of stuff going on, so capturing signals and different types of signals, especially types of signals that that you can actually classify, is quite difficult. So until I can get my hands on that remote radio, I'm just slowly building up my data set. But you might have some additional signals that you've captured that you'd like to add into the model. So it's quite simple. You can train from scratch, so create a whole new model if you like, or you can fine-tune the existing one, and that's what I'm going to do now. So because I'm running on Windows, I'm going to use this command here. So it's using the retrain model script that we downloaded into the Pycom directory, and it's using the fine-tune parameter, which means we're not building from scratch, we're adding to our model. And we're using the freeze classifier input flag, which freezes certain layers in the model so that your new signals won't necessarily outweigh the base training. So it provides a bit of balance. And there's different options available, which are documented in here, which I won't go into in too much detail. You can see what they are here. You can use Google or AI to understand them in a little bit more detail if you need to, but I'm just going to run this script here. So if I take that and copy that into my so if I hit enter, you can see that the script's running away, and it's found the additional captures that I have in my captures directory, and it's adding those captures to the model. So you can see the script provides a lot of information around what it's actually doing, so you can read through it to understand what it's doing if you need to. As I said, you can use the documentation or information that's available online to understand the different options and terminology if you need to. But you can see here we've trained over 30 epochs, so for every signal it's presented to the model 30 times, so that the model can it's like reading a book more than once. It compounds its knowledge and understand. It makes it understand the information that you're providing it so much better. And you can see here we've got a model accuracy of 70.43%, and that's based on the data that's been provided has got stuff that it's trained on, and it also uses a portion of your data for testing. So it's the split. I can't see where it's listed the split, but it should save a certain set of your maybe it says here only 3 samples. So those 3 samples, it got it right 70% of the time. I don't know how that works. Maybe I'm not reading that correctly. But it's made a good guess. But you also see here that I've got the additional auxiliary information included. So this dim is the 13 different auxiliary entries that have been added for each capture. So that was, if we go back to the documentation, that was those 7 new features plus where's my web browser? it was these 7 new features plus the existing 7 that were already in there. So it's gone through for each of the captures. It's gone through and made calculations based on the capture, what these additional features are, given them a weighting, and added them into the model. And I had span, reference level, noise floor, bandwidth, frequency offset, and signal to noise ratio, plus these 7, which makes obviously the 13 different pieces of auxiliary information that are added to each training run. So as you can see, the model was successfully built. So I can either restart Pycom, or I can open it up. Where is it? I can open up the configuration here, and I can go to signal detection, and I can come down here and click reload model, and so that will load the latest model into the system, and I can create another capture, and hopefully it would have learned a little bit more about the signals that you're seeing on the waterfall. I mean, obviously I've not added a whole heap of data, and that's obviously quite dangerous. You want to get a good data set to add to the model, but if I take a look at that signal there, it still thinks it's FM for some reason, but again, I can save that and tell the classifier that on the next run that that's in fact JT65. I know that the model didn't predict accurately on both these attempts, but it's getting better and better over time. I can see it, and when I do get my hands on the remote radio from my local amateur radio club, I'll be able to create a much bigger data set, and it will be that much more accurate. But that's it. This is the 101 for machine learning within Pycom. Have fun, and see you next time.